Guys, welcome back. So today we're going to do a worked example using bond enthalpies. So this is question number 4 on my set of my teacher's notes here. I think we did question 5 on the original video. So yeah, we did question 5 in the original video. So try question 4 for yourself now and pause for the worked solution. All right. So really, so the first thing you always want to do when do anything with bond enthalpies or you're asked about bond enthalpies is draw Lewis structures. So in fact, I would even go as far as to say don't use a chemical equation for it. Use Lewis structures H, or at least some sort of Lewis structure plus C triple bonded O. 2, 4, 6, 8, 10 yields C H H H C O H O. First, draw your Lewis structures. This will prevent you from making stupid, silly mistakes, because you can actually see what bonds you're breaking, see the bonds themselves, and how many numbers of them. There's my pointer. So I need to draw my lone pairs. Sorry. So now the official, the way you would do it is bonds broken, the sum of all bonds broken minus the sum of all bonds formed. And this would actually net out to be sum out to be R minus sum of P, reactant and product. Now, this is actually flipped from when we did product. This is actually flipped from formation enthalpies, which, as you may recall, is product minus reactant. What's the deal here? Now, in order to understand this, well, conceptually as one could get, I prefer to think of it as bonds broken minus bonds formed, because that's the difference. That gives you the difference in enthalpy, because it's the bonds you form. Because if you did form minus broken, you'd probably still get the same answer with the opposite sign, but since sign matters, it's more or less going back to the statement using Hess's law that bonds broken. It's similar to formation enthalpies in the sense that you're essentially breaking every single bond and then reforming them, and that's sort of where the formula comes from. That now that you're instead of going backward from a reaction from that the enthalpy change of formation of the reactants is the standard state elements to the 1 mole of reactant, you are now quite literally you're just breaking all those bonds in the reactant and forming and breaking every single bond in the reactant, and then you reform them. And sort of here, maybe if I draw a cycle, so R P E, where E is the elements. Now, when we did enthalpy change of formation, using formation enthalpies, we did product minus reactant because, we know that, okay, we know this is, say this is X, Y, and this would be X plus Y. So we use those sort of elements as an intermediate between the two steps. So it's the same sort of idea as we did with formation enthalpies, that okay, you're going from your standard state reactant to the elements and then to the product, and then similar sort of idea is when you with bond enthalpies, you're breaking all these bonds, so reactant to elements, so that's bond breaking, and then that's bond forming. So that's sort of why we work it the way we do. So with that in mind, now this is some pretty, now that sort of we have that explanation of the way, which I probably should have done in the original video. Oops, I hope I did anyway. If not, hopefully, well, it's better late than never. So now let's actually do the problem. So we have three CH bonds, and I now need to pull up a table of bond enthalpies. So allow me to quickly pull that up. Three. So 3 times a CH bond is, so looking here on my screen, CH is 414. 4. Or alternatively, there's another way you could do this, that so you can break all bonds plus, so you break down one CO bond, CO single, which is 358, plus one OH bond. OH is 463, 63 plus 1077. That was given in the question. So if I go back here, scroll, get 1072. Whoops. So that was 1072. And then if I did bonds formed, which is 3414 plus 1C00. So if I scroll up here, a C00 is C00 is 804. 804 plus 1 carbon-carbon single, which is 346, plus 1 carbon-oxygen bond, which is 1 carbon-oxygen, which is 358, plus 1 OH bond, which is 463, which yields us an answer of, let me calculate it real quickly, yields us an answer of negative 78 kilojoules. So, which yields us an answer of negative 78 kilojoules per mole. Now, you could take this whole bonds broken to bonds formed thing to a real extreme and really just analyze the bonds that were broken. So, you can actually simplify this quite a lot. We never really broke those bonds, so that goes away. We never really broke this OH bond here, so that can also go away. And the only things you really broke were, and you even never broke this CO bond, so that can go as well, this 463. The only bond you really broke was that one, and the only bond you really formed was those two, so you could just simplify your expression to 1072 subtract 804 subtract 396. Or so you could really just simplify your expression to that. And that's often what you see in the IB mark scheme, because you're really taking the whole bonds broken minus the bonds formed thing, quite literally. Now, you could break all the bonds and reform them all and you'll get the same answer. However, notice here that, even in this picture, this CH3 group stays the same. You can see that CH3 group stays. We can see that this OH group remains. Again, this OH group remains. And lastly, we can see that there's a CO bond that is there. We also see that that CO bond is there. Again, the only bond you really broke was that one, and you reformed that one and that one. So you could really just do that and call it there. Um, so that's a little life hack to really save yourself from all the calculations there. Hopefully this gave you a bit more insight as to how these things work. Thank you for watching. Don't forget to like and subscribe.